Okay, in this video we're going to describe the shapes of molecular orbitals and how they form bonds, meaning the pi and sigma bonds. We know that the atom contains the nucleus and the electrons surrounding the nucleus in clouds. Those clouds are of different levels, so we'd call them shells, and each of those shells has orbitals in them, which is the place where you can most likely find an electron. According to atomic theory and quantum mechanics, an orbital is a function that describes and predicts the location and wave-like characteristic of an electron in the atom. It's the probability of finding an electron around the atom's nucleus. That's what an orbital is. In layman's language, it's where the electrons are likely to be found around the nucleus. There are three types. There are several types. Let me say the overall there are like 5 of them, but the 3 that are most common to everyone is sp and d, although we do have f and g. The s will be spherical in shape across the Cartesian plane, and then the p will be like an 8 or an infinite shape with two lobes. So you can be the p orbital could be on the x-axis, or could be along the y-axis, or could be along the z-axis. And that's why we always say that the p orbital will carry a maximum of 6 electrons, because each will carry 2 electrons. Okay, so you have px, py, and pz based on the orientation on the Cartesian plane. The s orbital just carries 2 max, and that's it. Now, if you are on 1s, the s orbital will be smaller. If you are on first shell, the s orbital will be smaller. If you're on the second shell, it will be bigger because you're moving further away from the nucleus. If you're on the third shell, the s orbital will be even bigger. So you are comparing like an orange maybe to a small ball, maybe compared to a basketball or watermelon. All those are S's, and the size also changes significantly with the p's. The 2p, the first time you see the p orbital is on the second shell, the 2p will be smaller than the 3p, and so forth. Okay. So to form sigma bonds, it has to be head-head overlap. So if you take an s orbital and bring it real close to another s orbital, there's going to be a point where there's be an overlap. Where there's an overlap, that is where we say that there is bond formation. So like right there's a bond formed. Okay, bond formation. A typical example is hydrogen with 1 electron and another hydrogen with 1 electron. Obviously, those 1 electrons are in the 1s1. You must have already looked at or you've already learned about electronic configuration. So it's 1s1, 1s1. So these S's have a single electron. And when those electrons meet up, they make a bond. Okay, so like if let me clean up this place. So those 2 electrons will be converged right in the middle here in my illustration, right there, and that's where this electron sharing, you're gonna make a bond. So hydrogen and hydrogen combining will give you hydrogen with 2 electrons in between them. You get what we call a shared covalent bond. And because they were formed by head-head overlap of orbitals, that type of bond is called sigma bond. It's stronger than the pi. So when 2p orbitals match up their orbitals, meaning the shaded and shaded meet up constructive overlap, you're going to get another overlap there with the electrons if the electrons were residing on that area. of the p orbital. When they overlap, you get a pp, still sigma bond because it's head-head. It's like head-head collision of two vehicles, you know. Those collisions are very, very, very effective. The vehicle will end up being totaled or thrown away. Pi orbital is made by side-side overlap. I'll show you that. You can also have a ps or sp orbital where p orbital overlaps head-head with an s. You get a bond right there. When p orbital and s orbital overlap, you will get ps sigma bond. It's head-head. Sometimes you can have an hybridized orbital mix up of s and p orbitals. You get a hybrid orbital. The hybrid orbital could be sp3 or sp or sp2. So this is an example of how our sp3 looks like. We'll talk about it soon. When the two meet up, you get sp3 sigma bond where there's an overlap. When sp2 and sp2 meet up, you get sp2 sigma bond when they overlap. You see the sp2 will have a smaller lobe compared to the sp3, and sp will even have much smaller. That's how you can tell them apart for the hybrid orbitals. Okay, so if you take one s, let's describe formation of sp3 orbitals. If you take one s and combine it with different orientation of p's, you will get, overall, you will get what we call sp3. This one right here is an sp3. Is an sp3 where you have an s combining with the p3s, you get a new hybrid orbital sp3. The bond angle between them is gonna be 1 or 9.5 roughly, and a perfect example we usually give is of a carbon that has 4 hydrogens. We call that methane. So the knobs that will come out of the carbons are of a hybridized orbital because you're hybridizing, you're mixing up orbitals. General shape for an sp3 orbital is tetrahedral because of the different ways the single sp3 orbitals will be oriented in the 3D tetrahedral structure. When they are combined to give this structure, you end up with an overall sp3 tetrahedral 3D structure. Okay, so each time you have sp3 hybridization, know that when they mix up, when 4 of those mix up, you're gonna get a tetrahedral. When 4 of these mix up, you're gonna get tetrahedral shape, which is roughly something like that, or looking at orbitals will be like this with bond angle of 109.5. I've given you an example of CH3 of CH4. So methane will have a carbon that's gonna be sp3 hybridized. Okay, and then if you mix up if you mix up 2 sp3 orbitals, like if you combine them, only 2, if you bring them head-head on head-head combination, you get a sigma bond, and that type of sigma bond will be called sp3 sigma bond. Okay, and that could be illustrated if you have, let's say you have 2 carbons, like in organic chemistry. Let's say you have 2 carbons like this. We'll talk about hybridization later of bonds, but if this carbon is sp3 hybridized and this one is sp3 hybridized, then the bond between them will be sp3. That's what you are describing here. However, hydrogen only has one s. If this carbon is sp3 hybridized, then this bond will be sp3s. And you can quickly tell hybridization of this carbon, which we'll discuss in another lesson. The carbon here has 4 electron groups, electron groups in summary will include 1 sigma bond, 1 pi bond. This is the quickest way to determine the total electron groups, and then 1 lone pair, so 1 lone pair of electrons, and of course 1 triple bond. So on this carbon I see that I have 4 single bonds, so I have 4 electron groups. So I have 4 electron groups on that carbon. That can only be sp3 in theory, so that carbon must be sp3. Okay, hydrogen is S only because it has 1 electron in the 1s1. So if this is sp3, this will be sp3, and the bond between them will be formed by sp3 overlap, while the bond here will be sp3s. The bond here will be sp3s. Okay, all of them are sigma bonds, and I'm showing how they are placed in the tetrahedron to give you tetrahedral shape like what's shown here. Okay, and then for sp2, formation of sp2, you will need 1s and 2p's. 1s and 2p's, when they combine, they will give you what we call sp2. Okay, so if you take 3 each, this shows 3 sets of sp2s. When they are combined, they give you something that fits in a triangle, a group of the hybrid orbitals that fit in a triangle. So the molecular shape is trigonal and planar. It's flat. See how flat it is here, because this is the same as this structure right here. It's flat. See how flat it is. Fits in a triangle, but it's flat. Also shown in that way. If you tie up these 3 balloons, you get them like this, but they're flat. If you take 2 sp2 hybrid orbitals and let them overlap, if they have electrons in them, you're going to get an sp2 sigma bond. So there are so many types of sigma bonds. There's sp3p, sp3p, sp2, sp3. Here I've shown you sp2 sigma bond. Okay, if you combine an S with only one P, you will get sp orbital. When you get the sp orbital and combine those 2 sp orbitals, you're going to get this kind of a structure which has a bond angle of 180. So sp will always give you 180. I forgot to tell you, sp2 will always give you a bond angle of 120 degrees, but sp will give you a bond angle of 180. I told you sp3 will give you 109.5. Okay, so these hybridizations goes with the electron domains, and they tend to help you predict the bond angle. A perfect example of sp will be something like CO2. Remember the electron domains. I told you one electron domain could be a single bond, a double bond, or a triple bond. Here, I only see 2 electron domains. Since there are 2 electron domains, then I expect that this molecular geometry will be linear. There's no lone pair in the middle to repel. We'll talk about geometries in the next lesson. There's nothing to repel the electrons that are bonding, so it's straight line, and the bond angle is roughly 180. Okay, a perfect example for sp2 in this case will be something like formaldehyde, which has this kind of structure. This carbon right here has a double bond, single bond, so 3 electron domains. That has to be spp, so that carbon is sp2. And therefore, you can already predict that this bond right here is made from the S from the hydrogen at sp2 orbital from the carbon. That bond right there is an sp2 sigma bond. Okay, and so will be this sp2. For the double bond, one of them is pi. We'll talk about it next. We'll talk about that next. The other one will be sp2, sp2. sp2 from the carbon and sp2 from the oxygen. The oxygen has two lone pairs and a double bond. Those are three electron domains. So the oxygen has to be spp. So the oxygen is sp2, the carbon is sp2. The sigma bond, which is one of those double bonds, will be sp2, sp2. Will come from the sp2, sp2 combination of orbitals. The other bond is a pi, which is side-side overlap of pp. You see how here we have an hybridized p orbital, meaning it was not mixed with the other three spp. It's unhybridized. If it's unhybridized, it can meet up with another one that is unhybridized. When they are too close, when they do side-side overlap, shoulder-shoulder overlap, you're gonna get a pi bond, which we'll discuss next. So pi bond is formed when you have parallel, side-side or parallel p orbitals. When they overlap up and down, you get a pi bond. So this is what we call the pi bond. Pi bond is always formed by side-side overlap of orbitals. An example is whenever you have a CC double bond, one of them will be pi, one will be sigma. Now, if I have hydrogens here, just to wrap up the lesson, this hydrogen right here is an S, has an S orbital because it's one S obviously. But this carbon, because it has a double bond, single bond, it has 3 electron domains. That double bond, that carbon, this carbon right here will be sp2. So the bond in between is formed between an sp2 hybridized orbital and a sigma, and an sp2 hybridized orbital and an s orbital, and that gives you a sigma bond. So will this be an sp2 s sigma, and then the sigma bond here, both carbons are sp2. The sigma bond in between here will be sp2, sp2. The pi will be always from pp overlap of an hybridized orbital. Unhybridized because here you see sp2. The difference between sp2 and sp3 is a difference of just one p. That p is not mixed up to make any hybrid. It's available. And it's if the p of one carbon and the p of another carbon, which are always parallel to the hybridized ones, these are the ones that are hybridized. If those parallel p's overlap, that's how you get a pi bond. Okay? In between here, those will come from the sp2, sp2, which is what I'm showing right here and right there. Again, this sigma bond is from sp2s. Hydrogen brings the s, the hybridized carbon brings sp2. So with that, I believe at least you have an idea of what's going on with hybrid orbitals and how they are formed and how sigma bonds are formed.